Imagine settling into a quiet space where the gentle flow of thought guides you through the world of calculus. Tonight, we embark on a journey that weaves together the history, foundational ideas, and future possibilities of this remarkable branch of mathematics. With each step, the complexities of calculus will unfold in a calm and approachable way, inviting curiosity rather than worry. Let your mind relax as we explore the elegant patterns and profound insights that have shaped how we understand change and motion. This is a gentle invitation to discover the beauty and depth of calculus, one concept at a time. Picture Archimedes in the quiet city of ancient Syracuse, his mind wandering through the mysteries of shapes and spaces. With only simple tools and keen observation, he begins to unravel the secrets of area and volume. Using the method of exhaustion, Archimedes patiently divides figures into smaller and smaller pieces, inching closer to their true measurements. This geometric intuition lays the groundwork for what would one day become calculus, blending curiosity with careful reasoning. In the gentle glow of lamplight, the origins of a profound mathematical journey quietly unfold. Archimedes, one of the greatest mathematicians of antiquity, explored the area under a parabola by cleverly filling it with a series of triangles. He began by inscribing a triangle beneath the curve, then repeatedly added smaller triangles within the remaining spaces. With each step, the triangles became finer, gradually covering more of the area. This method allowed him to approximate the total area with remarkable accuracy, anticipating the modern concept of limits. Through patience and logical reasoning, Archimedes revealed how infinite processes could yield precise results, long before calculus was formally developed. Imagine a point moving ever closer to a destination, yet never quite arriving. This is the essence of approaching a value infinitely closely, a concept that forms the very heart of calculus. It allows us to explore what happens as numbers get smaller and smaller, almost touching zero, or as they grow without bound. By understanding this idea, we unlock the ability to describe change and motion with remarkable precision, even when dealing with quantities that seem impossible to measure directly. This foundational insight brings clarity to the patterns and rhythms that shape our world, inviting both calm reflection and deeper understanding. The concept of limits has a fascinating journey through the history of mathematics. Ancient thinkers first glimpsed the idea while grappling with paradoxes and the infinite. But over time, these early insights faded from collective memory. Centuries later, mathematicians rediscovered limits, recognizing their power to describe change and continuity with precision. This revival laid the groundwork for calculus, transforming not only mathematics, but also our understanding of the natural world. The story of limits is a testament to how ideas can be lost and found, continually shaping the path of discovery. Journeying back to the civilizations of ancient Egypt and Babylon, we find the roots of mathematical discovery woven into daily life. These early mathematicians developed ingenious methods for measuring land, calculating the area of fields, and determining the volume of granaries and pyramids. Their practical techniques, recorded on clay tablets and papyrus, reveal a remarkable understanding of geometry and arithmetic. Long before the formal invention of calculus, these civilizations laid the groundwork for the concepts that would one day evolve into integral calculus, using careful observation and logical reasoning to solve the challenges of their world. The Moscow Papyrus and Babylonian records stand as remarkable testaments to ancient mathematical knowledge. These documents reveal not only a surprising degree of accuracy in calculations, but also an early understanding of geometric summation. Through careful observation and methodical reasoning, ancient scholars were able to solve complex problems involving areas and volumes. Their work laid important foundations for later developments in mathematics, demonstrating that curiosity and logic have long guided humanity's quest to understand the world. Ancient methods often focused on addressing individual challenges, crafting solutions tailored to each unique situation. While these approaches were effective in their context, they rarely sought to uncover the broader principles that connected different problems. This meant that knowledge remained fragmented, with little opportunity for techniques to be applied beyond their original scope. Over time, the need to generalize and understand underlying patterns became clear, paving the way for more unified and powerful methods. Archimedes, one of the greatest mathematicians of antiquity, developed the method of exhaustion to calculate areas and volumes with remarkable precision. By inscribing and circumscribing shapes with polygons of increasing sides, he could approximate the area of a circle or the volume of a sphere ever more closely. This approach laid the groundwork for integral calculus, centuries before its formal development. Archimedes' insights also hinted at the concept of derivatives, as he examined how quantities changed in infinitesimally small increments. His pioneering work continues to inspire and inform mathematical thought to this day. At the same time as mathematicians in other parts of the world were making discoveries, Liu Hui in ancient China was quietly developing his own methods for calculating areas. Working with remarkable precision, Liu Hui explored geometric shapes, using logical reasoning to break them down into smaller, more manageable parts. His techniques, developed independently, mirrored those found in other cultures, highlighting the universal curiosity and ingenuity of the human mind. Through careful observation and methodical calculation, Liu Hui contributed significantly to the mathematical understanding of his era. Throughout history, the Islamic world has been a cradle of mathematical innovation. Among its most influential figures was Ibn al-Haytham, whose explorations extended far beyond optics. He made significant contributions to the understanding of polynomials and the early principles of integration, laying groundwork that would later shape modern calculus. His analytical approach and detailed methods inspired generations of scholars, demonstrating the profound impact of Islamic mathematics on the world's intellectual heritage. In the quiet landscapes of Kerala, India, a remarkable school of mathematics flourished centuries ago. Led by the visionary Madhava, this group of scholars delved deeply into the mysteries of numbers and shapes. Their work laid the foundation for infinite series and advanced trigonometry, long before these concepts appeared elsewhere in the world. Through careful observation and innovative thinking, the Kerala school illuminated new pathways in mathematical understanding, inspiring generations to come. The Kerala school of mathematics, flourishing in southern India from the 14th century onward, made remarkable advances in mathematical thought. They developed innovative methods to approximate the value of pi with impressive accuracy, centuries before similar techniques appeared in Europe. Their scholars also formulated infinite series expansions for trigonometric functions, closely resembling what we now call Taylor series. In addition, early notions of differentiation emerged in their work as they explored how quantities change and laid the groundwork for calculus. These achievements highlight the Kerala school's profound influence on the global history of mathematics. The journey of knowledge across continents has always been shrouded in intrigue, especially when we consider the development of calculus. In both India and Europe, mathematicians grappled with the infinite and the infinitesimal, often arriving at remarkably similar concepts independently. This parallel evolution raises questions about whether ideas traveled silently along ancient trade routes, or if human curiosity naturally led to these discoveries in different lands. The mystery remains, inviting us to reflect on the interconnectedness of human thought and the subtle ways wisdom can traverse boundaries, sometimes unnoticed. Although the Kerala school made remarkable advances in mathematics, they are not credited with inventing calculus. Their discoveries, while impressive, were often isolated and lacked the unifying framework that defines modern calculus. The concepts they developed were not generalized into a comprehensive system, and their methods remained fragmented. Without this broader synthesis, their work did not evolve into the unified theory that later emerged in Europe. As a result, the Kerala school's contributions are recognized as important steps, but not as the invention of calculus itself. Throughout history, the fundamental ideas of calculus have emerged independently in various cultures, revealing a universal quest to understand change and the infinite. Ancient mathematicians from Greece, India, China, and the Middle East each developed their own methods to tackle problems involving motion, growth, and the endless division of space and time. These discoveries were not isolated. Rather, they reflected a shared human curiosity about the patterns and rhythms that shape our world. The principles of calculus became natural tools, arising wherever people sought to describe the shifting and boundless nature of reality. This convergence highlights how deeply connected our intellectual journeys are, transcending borders and eras. As we move into Europe during the 1600s, a remarkable transformation begins to unfold. Mathematicians start to blend the abstract language of algebra with the visual clarity of geometry. This merging of ideas creates a fertile ground for new discoveries. It is within this evolving landscape that the foundations of calculus are quietly being laid, preparing the way for profound advances in our understanding of change and motion. René Descartes made a profound impact on mathematics by forging a connection between algebra and geometry. He introduced the concept of the coordinate system, a framework that allows geometric shapes to be described using algebraic equations. This innovation transformed abstract problems into visual representations on a grid, making them easier to analyze and solve. Descartes' approach laid the groundwork for analytic geometry, opening new pathways for scientific discovery and logical reasoning. Pierre de Fermat was a pioneer in the study of mathematical analysis, long before calculus was formally established. He developed ingenious methods to determine the highest and lowest points, known as maxima and minima, of various curves. Fermat also devised techniques to find tangents to these curves, laying the groundwork for what would later become differential calculus. His early approaches to integration allowed him to calculate areas under curves with remarkable precision. Through these contributions, Fermat set the stage for future mathematicians to expand upon the foundations of modern calculus. Imagine a quiet moment where the mind drifts back to the early days of mathematics. Bonaventura Cavalieri, a visionary of the 17th century, introduced the method of indivisibles, a gentle yet profound approach to understanding shapes and areas. By considering lines, surfaces, or volumes as composed of infinitely many indivisible elements, Cavalieri laid the groundwork for what would become the modern concept of integration. His method invites us to see the continuous as a harmonious sum of countless parts, each contributing quietly to the whole. In this way, Cavalieri's insight opened a new path for exploring the infinite, guiding us toward a deeper understanding of the world's subtle structures. Isaac Barrow was among the first to perceive a profound connection between differentiation and integration. He recognized that these two processes, though seemingly opposite, are in fact deeply intertwined. Barrow's insight laid the groundwork for what would later become known as the fundamental theorem of calculus. By understanding that differentiation and integration are inverse operations, he helped pave the way for future mathematicians to unify these concepts into a single, elegant framework. Isaac Newton was a remarkable thinker whose curiosity shaped the course of science. During the Plague Years, when universities closed and the world grew quiet, Newton retreated to the countryside. In this solitude, he developed the foundations of calculus, a mathematical language for describing motion and change. His mind turned to the mysteries of how objects move, accelerate, and interact, seeking patterns hidden within the chaos. These early insights would become the cornerstone of his groundbreaking work in physics and mathematics. Newton's method of fluxions, developed in the late 17th century, was a groundbreaking approach to understanding change and motion. By introducing the concept of instantaneous rates of change, Newton laid the foundation for what we now call calculus. Despite the significance of his discovery, Newton was hesitant to share his findings with the wider scientific community. His reluctance to publish stemmed from a desire for perfection and a fear of criticism, leading him to keep much of his work private for years. This secrecy would later contribute to disputes over priority, as others independently explored similar mathematical ideas. Gottfried Wilhelm Leibniz was a remarkable thinker who began his journey into mathematics later than many of his contemporaries. Despite this late start, his curiosity and determination led him to make profound contributions to the field. Leibniz approached mathematics with a unique perspective, focusing on the geometric foundations that underlie many concepts. Independently, he discovered calculus, developing his own methods and notations that would shape the way mathematics is studied and understood. His work stands as a testament to the power of fresh insight and the enduring impact of creative minds. Newton and Leibniz both developed calculus independently, yet their approaches reveal subtle but important differences. Newton viewed calculus through the lens of motion and change, focusing on the concept of fluxions, or quantities in continuous flow. In contrast, Leibniz emphasized the use of infinitesimals, and introduced a systematic notation that made calculations clearer and more accessible. This distinction in notation proved crucial, as Leibniz's symbols are still used today, shaping how mathematics is taught and understood. The clarity and structure of notation not only influence comprehension, but also the evolution of mathematical thought. In the late 17th century, Gottfried Wilhelm Leibniz published his innovative methods for calculus, introducing a clear and systematic notation that would become foundational for mathematics. His use of symbols like the integral sign and the differential d made complex calculations more accessible and easier to communicate. As scholars across Europe encountered Leibniz's work, they quickly recognized the advantages of his notation over previous approaches. This led to widespread adoption, allowing calculus to spread rapidly through academic circles and inspiring a new generation of mathematicians. The clarity and efficiency of Leibniz's system played a crucial role in shaping the future of mathematical analysis. The Newton-Leibniz controversy stands as one of the most significant disputes in the history of mathematics. Both Isaac Newton and Gottfried Wilhelm Leibniz developed the foundations of calculus independently, but accusations of plagiarism soon emerged. Supporters on each side fiercely defended their respective mathematician, leading to a deep rift within the scientific community. This divide was not just personal, but also national, with British and continental European mathematicians aligning themselves along these lines. The lasting effects of this controversy shaped the development and teaching of mathematics for generations. After years of heated debate, the mathematical community gradually acknowledged that both Newton and Leibniz had arrived at the foundations of calculus independently. This recognition helped ease tensions and allowed the focus to shift from rivalry to progress. Over time, Leibniz's notation, with its clarity and flexibility, became the preferred language for expressing calculus. Today, the symbols and methods he introduced are used worldwide, shaping the way generations of mathematicians and scientists approach complex problems. The resolution of this dispute stands as a testament to the collaborative spirit that ultimately drives discovery forward. The Bernoulli brothers, Jacob and Johann, were pioneers in the field of mathematics during the late 17th century. Their work on curves and optimization laid the groundwork for many modern mathematical concepts. One of their most famous achievements was the solution to the brachistochrone problem, which seeks the curve of fastest descent between 2 points. By applying innovative methods, they demonstrated how nature often follows paths of least resistance. Their insights continue to influence mathematics, physics, and engineering to this day. Leonhard Euler was a visionary mathematician whose contributions transformed the landscape of calculus. He introduced innovative notations that made complex calculations more accessible and intuitive, many of which are still in use today. Euler's work bridged the gap between calculus and the mysterious world of complex numbers, revealing deep connections that enriched both fields. His prolific advancements continue to influence mathematics, offering clarity and structure to concepts that once seemed abstract and elusive. Euler's formula reveals a profound connection between exponential functions, trigonometry, and the complex plane. It states that e raised to the power of an imaginary number, specifically e to the I times theta, equals the cosine of theta plus I times the sine of theta. This elegant equation allows us to visualize complex numbers as points on a circle in the complex plane, where the angle corresponds to the argument and the distance from the origin reflects the magnitude. Through this relationship, exponential growth and oscillatory motion become intertwined, offering a unified perspective on seemingly distinct mathematical concepts. The beauty of Euler's formula lies in its simplicity and the way it bridges different areas of mathematics into a harmonious whole. In the early days of calculus, mathematicians relied on the concept of infinitesimals, quantities so small they could not be measured, yet were not quite zero. This approach, while powerful, raised logical concerns about the foundations of calculus. The philosopher George Berkeley famously criticized the use of infinitesimals, calling them ghosts of departed quantities. He questioned how something could be both non-zero and yet vanish in calculations. Berkeley's critique highlighted the need for a more rigorous understanding of limits and continuity, which would eventually shape the development of modern calculus. Augustin Louis Cauchy and Karl Weierstrass played a pivotal role in transforming calculus into a precise and reliable field of mathematics. Before their work, calculus relied on intuitive notions that often led to confusion and paradoxes. By introducing the concept of limits, they provided a rigorous framework for understanding change and continuity. Their methods replaced vague ideas with clear definitions, ensuring that each step in a calculation could be justified. This foundation continues to support the study of mathematics, offering clarity and confidence to those who explore its depths. To truly understand calculus, it's important to explore the epsilon-delta definition of limits. This precise approach allows us to describe how functions behave as they approach specific points, using small distances called epsilons and deltas. Alongside this, the Riemann integral provides a rigorous way to measure the area under a curve by summing up infinitely many tiny rectangles. Together, these concepts form the logical foundation of calculus, bringing clarity and structure to the study of change and accumulation. As you relax and let your mind wander, imagine these ideas gently fitting together, building a harmonious framework for understanding the mathematics of the world around us. By the late 1800s, calculus had matured into a logically robust and practical mathematical framework. Mathematicians refined its foundations, addressing earlier ambiguities and ensuring that its principles rested on solid logical ground. This rigorous approach allowed calculus to become an essential tool, not only for mathematics, but also for physics, engineering, and many other fields. Its completion marked a significant milestone, providing clarity and reliability for generations of thinkers and innovators. Now, as we move from the fascinating history of calculus, let's gently enter the world of its core ideas. At the heart of calculus lies the concept of limits, a way to understand how things behave as they approach a certain point, without necessarily reaching it. Imagine tracing a line that gets closer and closer to a boundary, feeling the anticipation as it nears, but never quite touches. This simple yet profound idea forms the foundation for everything that follows in calculus, opening the door to new ways of seeing change and motion. Imagine standing in a quiet room, facing a wall just a few steps away. With each step you take, you cover half the remaining distance between you and the wall. As you continue, your steps become smaller and smaller, yet no matter how many times you repeat this process, you never quite touch the wall itself. This gentle approach illustrates the concept of a limit, getting infinitely close to a point without ever actually reaching it. In mathematics, limits help us understand how values behave as they approach a certain boundary, much like your careful footsteps toward the wall. Imagine a function as a smooth, winding path on a graph. As we move along this path, getting closer and closer to a particular point on the horizontal axis, we notice the function's values begin to settle near a certain number. In mathematics, this behavior is described by the concept of a limit. The limit tells us what value the function is approaching, even if it never quite reaches it. This idea helps us understand how functions behave near specific points, offering clarity even when the function itself is undefined at that exact spot. Limits give us a gentle way to explore what happens to a function as it approaches a particular point, even if the function itself isn't defined exactly at that spot. Imagine tracing a smooth path toward a gap, observing how the values behave as you get closer and closer. Through limits, we can describe the trend or tendency of a function near points of discontinuity or undefined values. This approach helps us understand and predict the function's behavior, offering clarity where a direct calculation might not be possible. In this way, limits become a powerful tool for making sense of the seemingly undefined. In calculus, it's essential to understand the difference between approaching a value and actually reaching it. When we say a function approaches a certain value, we mean it gets infinitely close, but may never truly arrive at that exact point. This subtle distinction is the foundation of limits, which allow us to analyze behavior near a specific value without requiring the function to be defined there. Recognizing this nuance helps us make sense of concepts like continuity and instantaneous rates of change, deepening our understanding of how mathematics describes the world. As we explore limits at infinity, we begin to understand how functions behave when their inputs become extremely large. Imagine following a path that stretches endlessly, observing how the function responds as you move further and further along. Some functions may settle toward a specific value, while others might continue to increase or decrease without restraint. By studying these patterns, we gain insight into the long-term tendencies of mathematical relationships, revealing a sense of order even as numbers grow without bound. Indeterminate forms such as 0 divided by 0 often appear puzzling at first glance. These expressions do not have a clear value, which means they cannot be evaluated directly. In mathematics, algebraic techniques are used to resolve these forms, often by simplifying expressions or applying limits. By carefully analyzing the structure of the problem, we can uncover the underlying patterns and find meaningful solutions. This process transforms confusion into clarity, allowing the mind to settle and rest as complex ideas become understandable. L'Hopital's rule offers a gentle and systematic approach to evaluating limits that present themselves as indeterminate forms, such as 0 divided by 0 or infinity over infinity. By focusing on the behavior of the derivatives of the functions involved, this method allows us to transform a challenging limit into a more manageable one. Instead of struggling with complex algebra, we simply differentiate the numerator and the denominator, then reevaluate the limit. This process can be repeated, if necessary, until the indeterminate form is resolved. Through this technique, what once seemed unsolvable becomes clear and approachable, guiding us calmly toward the answer. At the heart of calculus lies a remarkable number known as e. This constant emerges from a special limit. As we take larger and larger values of n, the expression 1 plus 1 over n, raised to the power of n, approaches e. This elegant limit not only defines the number e, but also forms the foundation of the exponential function. The exponential function, in turn, plays a crucial role in describing growth, decay, and many natural processes. Understanding this limit reveals the deep connections between algebra, analysis, and the patterns we observe in the world around us.